Right. Welcome to July 23rd class meeting. We're going to be talking about chapter 17 today, which is thermochemistry, thermodynamics, how heat moves around, and how we use that to understand chemistry in terms of chemical reactions, in terms of phase changes. How do we measure that? What are the units? That kind of stuff. So if you guys want to get right into that, we will. So first off, the first thing we're talking about is what's called specific heat. And this is going to be kind of our basis for understanding about how the heat moves. And so to understand how heat moves, we need to know how the energy of something is transferred. And so that's going to give us this conversation on what we call specific heat. So first off, to define some stuff, what the heck are we talking about when we're talking about energy? So we're going to use our physics definition for energy, and that is the ability to do work or make heat. Now, when it comes to chemical reactions, so the work would be considered, the rearrangement of the molecules, but you also might exert a pressure, and that pressure could be used for work. Or you might have a volume change, and that volume change could be used for work. Work is going to be some sort of, physical pushing, pulling, that kind of thing. And then it's just get hot or get cold. And this is what we mean by produce heat. And so if something is said to have energy, it can do this. So then when you talk about the two different types of energy, we call things potential energy and we call things kinetic energy. So potential energy is like if you think about a ball, if you hold the ball up in your hand, it has gravitational potential energy because the gravity is going to pull on that ball once you let it go. But as soon as you let it go, it now has kinetic energy due to gravity because it's moving through the air. So that's what it means by potential versus kinetic. That's about as simple as a model as it gets. In chemistry, we're interested in what's called like chemical potential energy. So the bonds hold the chemical energy, and when you rearrange those bonds, the resulting energy might be more or less than where you started. And so this is the chemical potential energy. It might result in kinetic energy. It might just simply result in heat. So this leads us to the first law of thermodynamics, is that all energy is finite, and so you cannot create energy or destroy it. You are just simply changing its form. Now, when we talked about the law of mass, we said mass can't be created or destroyed. And we found out that you could eventually create mass in nuclear decay. You could destroy mass. But what you were actually doing to it is you were converting it into energy. That's what Einstein's theory of relativity states. So it turns out it's energy is the thing that cannot be created or destroyed, that all energy is just simply changing forms. So then we can keep track of it in chemical reactions to understand things like phase changes, why things burn by just simply getting started, and why some reactions need to be slowly kind of kept going over time to make sure that they actually work. So when we talk about chemistry, we usually like to follow heat because most reactions or most processes are going to deal with heat more than they're going to deal with work. So what is heat? Heat is energy transfer. And so the way that we monitor energy transfer is usually by measuring temperature change. That is the easiest way for us to measure energy transfer is with temperature change. But if you guys remember, temperature is average kinetic energy. So we call heat Q, little q. And again, physics gives all kinds of letters to all kinds of stuff. Why not little h? Well, that's Planck's constant. Okay, so we got to use a different letter. Why not big H? Well, that's going to be something called enthalpy. Yeah, I know. So we're going to call it Q because it makes complete sense. So anyway, you've probably heard of calories. Well, calorie is a way of talking about energy transfer, and it has to do with temperature. And it's actually a metric unit. So in the United States, we talk about not using the metric system, but a calorie is actually a metric unit. But calories are based off water. So to have an energy unit that is based off everything, we use what's called the joule. And you guys will remember the joule from when we talked about light. The energy in light was measured in joules. So what exactly is a calorie? What exactly is a joule? And so the definition of a calorie is the amount of energy it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Because remember, we're monitoring heat, Q, by the amount of energy it takes to change the temperature of that substance. So when they first started, obviously, studying this stuff so long ago, water is a great example because they were using water for everything. And so they measured the energy it took to change the temperature of the water by 1 degree. If you have 1 gram of water and you go from 0 degrees C to 1 degree C, that's 1 calorie. If you have 2 grams of water and you do that same temperature change, then you have 2 calories. Now, calories are extremely small. So when you guys think of calorie, you're probably thinking of food calories, and you can expect like an In-N-Out burger to have 350 calories. Well, that means that if it was a regular calorie, then all one In-N-Out burger could do was take 1 gram of your water and change it by 350 degrees Celsius, or take 350 grams of your water and change it by 1 degree Celsius. That would not keep you warm. And so there must be something going on with those calories. And the answer is calories are actually food calories, and they equal 1,000 calories. Your body, if you're a typical, 100-pound to 150-pound teenager, maybe you are 200 pounds, that is going to be anywhere between 50 and 100 kilograms. And so you're going to need about 1,200 to 1,800 food calories just to maintain your body temperature throughout the day. And especially if you're in a colder climate, you'll burn more energy trying to keep yourself 98.6 degrees. If you are in a hotter climate, you also burn energy, but that's because you're trying to remove that extra energy. A little less easy to calculate because there's the whole sweat production that is not included in our basic calculations here. So now I told you that the calorie is based on water, so they needed something that's based on everything, and that was the joule. But you can easily convert calories and joules. 1 calorie is 4.18 joules. Joules are used for everything. They talk about every type of energy. So if you have 1 calorie, you have 4.18 joules. Calories are used for water. That's why when we talk about food, we're usually interested in how the food is going to affect the human body. The human body is mostly water, so we can use calories. But for the sake of most chemical processes and physical processes, we're going to be talking about joules because they might not involve water. So this leads us to a question then. Okay, water, the amount of energy that it takes water to change by 1 degree Celsius is a fixed amount called the calorie. But what about other substances? Do they have a fixed amount of energy it takes them to change 1 degree Celsius? And the answer is, yeah, they do. So the calorie is actually what we call the specific heat of water. That is the amount of energy that it takes to change the temperature of 1 gram of that substance by 1 degree C. So the definition of calorie, which includes water, the definition of specific heat is just remove the water and say any substance. Now, you've all experienced specific heat in your life. A great example of this is if you've ever been in a sauna. What is a sauna made out of? It's made out of wood. And the reason for that is we want to use a substance with a very high specific heat. Because what this means is the amount of energy that needs to be added to that substance to get it to change temperature is very high. So when you touch the wood, it is still be able for you to touch it, even though you've been pumping a huge amount of energy into that sauna room. So this is what we mean by high specific heat. It takes a large amount of energy for you to change the temperature of it. If you were to make a sauna out of aluminum, you wouldn't even be able to go in that room, let alone be able to sit down. You would burn yourself very quickly. And that's because things like metals have very low specific heats, meaning even a small amount of energy can change their temperature very quickly. So because of this, specific heat is a physical property, just like boiling point, melting point, that kind of stuff. If you have a substance and you know its specific heat, you can identify that substance because that is a property that is unique to it. And one way that we use this is when we're trying to identify metals. Say you were out and you were panning for gold in a stream and you found a bunch of metals that sank to the bottom and you wanted to figure out if they were gold or not because you couldn't quite tell. Most of the time when you pan for gold, it should look like gold, but so you couldn't tell. Well, what you could do is you could find the specific heat of that substance, and we'll show you how to do that today. And then that would tell you if it was gold or not. So, basic definition of specific heat. And water specific heat is 4.18 joules per gram degree C. And that's why 1 calorie is considered the specific heat of water, because they are the same thing. All right. So if we're going to be talking about the total amount of heat transferred, we're then going to be talking about the specific heat, which is given the symbol C, multiplied by how much you have of it, and how much temperature change you want to enact. So let me show you. Say, for instance, we had some water. Say, for instance, we decided to take a beaker full of water and we put 200 grams of water into the beaker and we're going to heat it up on the hot plate. And we want to bring this water to boiling. Right now, the water is at 25 degrees C, and we want to bring the water to 100 degrees C. And we're interested in how much energy it will take to change the temperature of the water from 25 degrees C to 100 degrees C. So we can use the equation. The Q, which is the total energy, so total energy, so we'll write it down here. The Q is equal to C, and C is specific heat. Times the mass. And then times triangle T. And triangle T means delta T, which means temp change. And it's very important that it is the final temperature minus the initial temperature. This might mean we have a negative temperature change. This might mean we have a positive temperature change. This will change the value of Q. Positive Q meaning energy in, negative Q meaning energy out. And that comes from this delta T right here being positive or negative. So now let's go ahead and plug in our numbers here. We want to know the total amount of energy it's going to take this water. This is H2O. So we need the specific heat of water. Now, if you remember from what we just said, the specific heat of water is either 1 calorie per gram degree C if we wanted our answer in calories, or it's 4.18 joules if we want our answer in joules. Most of the time, we're going to talk about joules. So that's specific heat of water. That's how much energy it takes to raise the temperature of 1 gram of water by 1 degree C. So you need four of these by 1. Okay. But we don't have 1. We have 200. So we're going to multiply that by 200. Notice that'll make the grams go away. And now we're going to have our temperature change. And remember, it's the final temperature minus the initial. So we're going to do 100 degrees C minus 25 degrees C. So we're going to get a temperature change. We're going to get a delta T of 75 degrees. Now we're just going to plug in all these numbers. Now, the nice thing about, this unit is that the calculator work is a lot better than last unit because it's, really just multiply, divide, that kind of stuff. The more important thing is like the algebra in here, but in this case, there's no algebra. So let's just plug in the numbers. 4.18 times 200. And then we're going to multiply that by 100 minus 25, which is 75. So 62,700 joules. Joule is J. You could also write this as 62.7 kJ, so kilojoules. If you want perspective on joules, you want to kind of understand how big they are, a nuclear weapon would be measured in the gigajoules, so the billions of joules and things like that. So a calorie, if you're eating a candy bar, you might have 200 to 300 calories in that candy bar. Well, that's 200 to 300,000 calories. Remember, because food calories are 1,000 calories. And then you would multiply that by 4.18 joules. So in the case of this thing, the amount of energy it takes for us to boil this water or bring it to 100 degrees C is way less than a candy bar that you would eat. So pretty cool. Now, I said that we could use this to identify metals or anything really. Well, how could we do that? Well, say for instance, we had the ability to tell the temperature of something, like an infrared thermometer, or maybe we could, touch it with the thermometer. And we found ourselves a piece of metal. Boop, boop, boop. And it kind of looked like gold. And we're like, okay, that's kind of looks like gold. And we look up the specific heat of gold, and the specific gold is like 1.9, I think, joules per gram degree C, or 0.9. Let me look it up. And again, these are all their specific heat of gold. These are physical properties. There you go. That's specific gravity. We want specific heat. Specific gravity is the same thing as density. Heat. I got it off by point. Yeah, I was off. All right. I'm always off. So gold, AU, is equal to 1.29 joules per gram degree C. Where's that calories? No, it's joules. Okay. And so what we want to do is we're going to heat this thing up, because we're going to say, okay, say we added 20,000 joules to this. And we want to know what the specific heat of this metal is. And say the metal is pretty small, it's about 10 grams. And when we did that, we noticed that the temperature change for this piece of gold, when we added 20,000 joules, the piece of gold went from room temperature up to about 350 degrees. So room temperature is 25. So now what we can do is we can say, okay, the specific heat is going to be the 20,000 joules divided by the 10 grams, and then multiplied by the temperature change, which is 325 degrees C. Notice that this gives us joules per grams degrees C, which is the unit for specific heat. So let's see what this stuff is. So 20,000. And then we're going to divide that by, and again, this is where your algebra skills come in, 10 times 325. So this is a specific heat of 6.15. So this probably isn't gold. This is more specific heat than wood. So this is probably something that's just spray painted gold, if we didn't just straight up melt it. So this is what I mean. This is the number we should get, and this is the number we did get, so we know this isn't gold, and this probably isn't even a metal at all. As if we looked up metal specific heats, they're extremely low. But notice that all of these heating, so when Q equals positive, that's going to be heat into the substance, so that's going to be endothermic. And notice when we're talking about heat out, if we were to let this thing cool and we were interested in the amount of energy that went into the air, if cooling would make this go from 350 back down to 25, and so that would be a negative change. So when when Q is negative, that's heat out. And that's what we call exothermic. Oh, my R and my M blending together. So why doesn't your coffee just spontaneously make itself? Is because the water wants to be room temperature. And so when you heat up your coffee, your water, you have to add heat in, the endothermic process. But when you just let your coffee sit there, it slowly gets cold. And that's because the exothermic, it's going to give that heat back to the surroundings. Pretty cool. So this is the specific heat equation. And what it tells us is the energy it takes to change the temperature of something. So how is that important? Like, how would you need to use that? Well, like I said, you can use it to identify substances, but you could also use it to look at things like chemical reactions. And so how do we do that? We use something called a calorimeter, or a ball calorimeter, a bomb calorimeter. And basically what you do is you take water and you put whatever you're trying to do inside of the water, whether it's a reaction or whether it's just a piece of metal. In the case of that piece of gold, we could have just tossed it into water. And what we see is we call this thing here, we call this the system. Right here, system. And we call everything else the surroundings. So if we control the system by isolating it, and we then control the surroundings by making it water or making it something else that we know the properties of, then what we can do is we can say, okay, the amount of energy that will be produced in the system will then have to be given to the amount of energy in the surrounding. So if the system loses energy, so if the system has a Q that is negative, then the surroundings energy will be positive because it's going to gain that energy. Or vice versa. If we have a system that is going to gain energy, then it's going to have to lose it from the system. So basically, the negative Q of one thing will equal the Q of another thing. Whether that is system or surroundings, that is interchangeable. So specifically in a bomb calorimeter, we're going to do a chemical reaction, or we're going to put a hot piece of metal. So we're going to have our system lose energy. So the negative Q of the system will be equal to the Q of the surroundings. And that's a G. The Q of the surrounding. Now, why is this helpful? Because remember, we defined what Q was. It was specific heat times the mass times the change in temperature. Specific heat times the mass times the change in temperature. So say we know that the system is an exothermic reaction. Say we put some octane in there. What is octane? 18. And we burn the octane inside of our water system. And we find out that the water, we want to know how much energy, what is the Q of the octane. So what we could do is we could monitor the temperature of the water, because that's 4.18 joules per gram degree C, because we know that. We could monitor the mass, say we had 500 grams of water in there. And what we could do is we could look at the temperature change that occurs in the water, because the positive value of this is equal to the negative value of that. And so what that would tell us is how much energy was released in this reaction. And so say our water was, got to 90 degrees C from room temperature. Maybe it was cold in that room. So now that we know the negative Q of the combustion of the octane will be equal to a number that is easily calculated by just measuring the mass and measuring the temperature. And then times 90 minus 20 is 70. We had 117,040 joules. So what this means is that we could then find the specific heat of the octane. We could find the temperature change of the octane. We could find the mass of the octane, because now we have a number that we can plug into this reaction, or to this CQ equals CM delta T. And all we had to do was measure one of the things in our experiment, whether that was the system or the surroundings. So we use this for all kinds of things. Basically, if you're looking at your food, calories, where did they find that number? And the answer is they used this device. They would take, say for instance, a Snickers bar, and they would put it into a chamber, and they would burn it. And they would try and get that chamber to distribute its energy very evenly to a big tank of water. They could measure the difference in energy in the water, and then they could figure out how much Q was in the Snickers bar when it had a complete combustion. Now, there are flaws with this system, because we need to get the energy transferred from the system to the surroundings. But also, remember that we have to completely isolate this. So if the water is not completely isolated from everything else in the universe, then it will lose energy to that system, or to the surroundings even further. But it's, pretty accurate. So a good way then to look at finding something like the specific heat of a metal that you didn't know, you could just simply get it hot and then drop it into boiling water. Here's the thing I was talking about. And you could, if you knew the mass of the metal, if you knew the change of the temperature of the metal, then you could find the specific heat of the metal because of the fact that you knew the specific heat of the water, the mass of the water, and the change in temperature of the water. So a few years ago, I found a piece of metal in my backyard, and it looked like just a regular old piece of metal, but it was pretty dense. And when I found its density, it came out to 8.9. And the problem with 8.9 grams per milliliter is when you look up pure metals, it just didn't really show up. The 8.8 is copper, but this didn't really look like copper. 9.1 is bronze, but didn't look like bronze. And then there was something like nickel was in the 8s as well, but it wasn't anywhere near that. And so what did I do? What I did was I heated up the piece of metal and I found its specific heat. Specific heat, like density, is a physical property. But if an alloy, which is what I anticipated this metal was, is mostly one of those particular metals, then that number will be kind of closer to its specific heat than the other ones changing it very much. So it turned out that it was mostly nickel with some zinc added in. And because of their specific heats being very similar to each other and their densities being very different from each other, that's what the density conversion was messed up. But the specific heat one was able to point me to a particular alloy of zinc and nickel. And it was just a blank that was probably used for holding down curtains or something. It wasn't worth anything at all. Disappointing. So, like say for instance, you're interested in looking at how hot is red hot. You could use a bomb calorimeter for that. You could heat something up, drop it in the water, and as long as you know the initial temperature of the water and the final temperature of the water, you could then find the final temperature of the very hot substance. So, pretty cool. But here's the problem. If we start graphing, for instance, water, and we're looking at the amount of heat that's in the water, so Q in joules, versus temperature. If we start down here and we go into, well, here. Let's make this even simpler. Let's measure the temperature over time. Okay. If we go down here and we're in like negative 100 degrees C, if we have gotten a piece of ice down to negative 100 degrees C, we put it in a negative 100 degrees C freezer, and we start to heat it up. Say we put it in a hot plate. If we monitor the temperature, we're going to see something weird. So here's 0 degrees C, and then here's 100 degrees C. What we're going to notice is that the water is going to go like this, and then as soon as it hits 0 degrees C, the temperature won't change for a while. Then all of a sudden, temperature will start changing. And then as soon as it hit 100 degrees C, the temperature won't change for a while. And in this case, water's plateau is way bigger than that one. And then after a while, you'll notice the temperature starts to go up again. And if you notice, 100 degrees C and 0 degrees C, this guy down here is the freezing point. And this guy right here is the boiling point. So what's happening here? What's happening here? If we plug in the numbers and we look at this right here, and we look at this right here, and we look at this right here, when we look at that, it turns out that that equation is very easily described as Q equals Cm delta T. But when we look at these plateaus, they're flat. And if you guys know, when it comes to talking about the graphs of lines, you know, a slope needs to have, you know, some rise over some run. And the rise and run has occurred because we have a delta t. And remember, delta t is final minus initial. So we have rise, we have over run. But what is going on here where it goes flat? What's happening here? What's happening here? We're still adding energy because it's sitting on the hot plate. But the temperature isn't changing. So delta T drops to 0. Well, if we plug 0 into our equation, that would just make it equal 0. And we know that's not the case. And so what this gives us is our first look of something called heat of fusion and heat of vaporization. Down here we have heat of fusion, and right here we have heat of vaporization. Remember when we talked about intermolecular forces? Well, one of the ways that water was super unique was because of the hydrogen bonding in the water. And this graph right here really showcases the strength of those hydrogen bonds. You'll notice that the plateau here is smaller than the plateau here. That translates into the amount of heat it takes to transfer water from a solid to a liquid. Solid to liquid is much less than the heat that is required to go from a liquid to a gas. Heating up a substance through its phases of matter tells us about the power in its intermolecular forces. The amount of energy, heat, is required to go from solid to liquid, or vice versa. It's called the heat of fusion. And it doesn't have a delta T, because what's occurring during this transfer is the energy is being used to break those intermolecular forces. So when it comes to solid to liquid, water has a low heat of fusion because it will be transitioning from weak forces that are in its solid structure to the hydrogen bonds that will be in its liquid structure. And so its heat of fusion is low. Water likes to melt. But water has a hard time boiling. And we use this all the time in our cooking. We can turn the water on, we can bring it to a boil, and we can let it sit there for a very, very long time. And the reason for that is we're breaking up those hydrogen bonds. We call that the heat of vaporization. The more water you have, the more heat it will take for it to vaporize. So before, when we asked ourselves the question, how much energy would it take to change the temperature of the water from like 25 degrees C to 100 degrees C, we use Q equals Cm delta T. Because you'll notice that if we're looking at our graph, our experiment existed in only this area in the water. We didn't break any intermolecular forces. We were already a liquid, and we were bringing it to 100 degrees, but we weren't going to then just continuously heat it up. We were just going to get to 100 and stop. So then how do you calculate something that says, okay, how much energy does it take to take a piece of ice at negative 20 degrees C? Say we have a 200-gram piece of ice, solid, and we're interested in bringing that up to like 200 degrees C. We're going to boil it and then continue to heat the steam way past its boiling point. Well, to do that, the total heat, so the Q total, will be equal to the Q of the ice temperature change plus the Q of the heat of fusion. So we'll say heat of fusion here. Plus the Q of the water, plus the heat of vaporization, and then plus the Q of the steam. And so we would have to add up all of those different equations to find the total energy. Now, this is a lot of work and it takes a lot of time. So while your homework, your classwork, has some examples of this, I don't need you to do that on the test. Okay, it's not on the quiz. All I ask you to do is be able to identify on a heat curve. So what's going on? So on the quiz, it'll ask you, it'll bring this up and it'll say like, what's happening at this plateau? What's happening at this plateau? Your homework wants you to do the calculations. So like, for instance, the energy change here, multiplying them all together. If you guys don't want to do that, that's fine. So here's a good example of that. We have a negative 10 degrees C piece of ice. We're going to bring it up to 140 degrees C. So what we're going to have to do is Q equals Cm delta T plus Q equals the mass times the heat of formation. Chegg. Boy. And then plus another Q equals Cm delta T plus the heat of fusion plus the heat of vaporization, and then multiply that by the final change. Now, you'll notice in this picture, it gives you the heat of fusion in kilojoules per mole, and it gives you the heat of vaporization in kilojoules per mole. So what that would have us do is, again, an extra step where we would have to turn our 200 grams of water into moles so that we could use the known value for the heat of formation and the heat of fusion that the book gives you. So not only are we doing 5 problems here to get the total number, but we're also having to do a molar conversion on top of that. It just becomes a lot of work, and for the sake of time, you guys don't need to do it. What you guys do need to know is what is the heat of fusion, what is the heat of vaporization, and how to read this graph. But I'm not going to ask you actually how to calculate it. So don't worry about that. If you want to do it, it's fine. It's really simple. You just add everything up. So if we were to do if we were to do the math on this, then our Q total would be equal to the Cm delta T of ice. And you'll notice that ice has a different specific heat. It's not the 4.18, it's a 2.09. So we'll have to look up the specific heat. So that would be 2.09 joules per gram degree C. We would then multiply that by the 200 grams of our ice and our temperature change. And our temperature change is -20 to ice's temperature, which is 0. So minus 20, so plus 20. So that would be the Q equals Cm delta T of the ice. Then we would have to add to that the specific heat measurement, which is going to be the mass, which in this case is 200 grams, multiplied by the heat of formation, or the heat of fusion. But in this case, the grams will have to be turned into moles. So we'll have to plug in the 200 grams divided by 18.0 grams per mole, multiplied by the heat of fusion. The heat of fusion for water is 6.02 kilojoules per mole. And again, this is why I'm not going to have you guys do this, because kilojoules, this number's in kilojoules, but this number's in joules. So we'll have to do a step at the end where we convert everything to kilojoules or convert everything to joules. And again, that's why I'm not making you guys do this at home. Now we're doing the temperature change from 0 to 100. So that would be our 4.18 joules per gram degree C, and then times our 200 grams, and then multiplied by the temperature change, which in this case will be 100 minus 0, so 100. And then we'll add to that the 200 grams divided by the 18.0 grams per mole. But now we have the heat of vaporization, which is 40. So we multiply that by 40 kilojoules per mole. So again, we need to convert this at the end. And then finally, we're going to be going up to 200 degrees C. So then we would multiply that by the steam specific heat, which is 2. So 2.0 joules per gram degree C, multiplied by the 200 grams, and then multiplied by our temperature change of 200 degrees C minus 100 degrees C. So again, all that work just to be able to do it. But again, at the end, we're going to have to do a conversion from kilojoules to joules or from joules to kilojoules. So this is why I don't ask these things on your homework and why I don't ask them on the test. Even though your classwork has some examples of calculating these heats, don't worry about it. It's not on the test. All I want you guys to be able to do is know which equations would solve, but that's it. So like this, the slopes are Q equals Cm delta T. The plateaus are heat of fusion. So it's just adding them all together. So you guys don't have to do this crazy math. Again, not difficult math, just too much of it. Okay. And that's most of the stuff we're going to talk about in chapter 17. But you'll also notice that we have Hess's law and something called enthalpy. So enthalpy is just the measure in heat. And because I posted it on here, it changed the delta to a thumbs down. So delta H, not thumbs down H. There it is. Why is it thumbs down? That's really funny. So anyway, enthalpy is just a fancy word for talking about heat. So the measure of thermal energy lost or absorbed during a chemical process is called enthalpy, but that's really just heat, okay? And so we call that delta H. So the amount of heat lost in a chemical reaction is going to be the heat of the products minus the heat of the reactants, or in this case, the enthalpy. And so the reason why we talk about heat lost, heat gained, and we talk about delta H versus H is because H is notoriously difficult to measure. If you have a pile of sugar sitting there, it's just sitting there. How much enthalpy does it have? How much heat does it have? Because remember, we measured all that stuff by changing of temperature. So we can't really know the H. What we can know is the change. We can look at the before and the after. And so we talked about Q positive being endothermic and Q negative being exothermic. Well, we can also just translate that into delta H. If the change in the chemical reaction results in a positive change, then that means that the energy had to go into the system. If the change in the energy is negative, it gives off energy, then that's exothermic. So endothermic reactions get cold because you are the surroundings. And so if you're touching that chemical reaction, it's going to take your heat. Exothermics get hot because if you were to touch that reaction, it would give you heat. And what your body is actually telling you is heat in versus heat out. So, and then it talks about a bunch of different examples. What I'm interested in is the graphs, which it doesn't show you. Okay, so if we were to graph delta H, okay, or sorry, H, versus time for a chemical reaction, when the reactants have more energy than the products, we have an exothermic process. Unfortunately, though, when we monitor this, what do we notice is that over time, we actually have to put a little bit of energy in, and then the energy goes down. We still have an overall change right here of delta H equals negative. So we still have an exothermic reaction, but we had this little bump here. And this little bump here is called the activation energy. We needed a little bit of energy to get the ball rolling, but as soon as the got to that point, it produced enough energy to kind of drive itself. And that's why this is considered an exothermic reaction, because the change in H is negative. We still had to have some activation energy, but not very much. If we compare this to an endothermic graph, the reactants will have less energy than the products. But if we monitor it, we'll notice it still does that hill. In this case, we now have a delta H equals positive. This is an endothermic reaction. But notice our activation energy now is very large. The book will later go on to talk about spontaneous versus non-spontaneous. And one of the big factors when it comes to whether reaction wants to drive itself is that the delta H tends to need to be negative versus delta H equals positive. And the reason for this is you have to put all the energy into the system to actually get the reaction to change, but you also have to overcome the activation energy as well. In this case, we're going to get our activation energy back. So the energy put into the system is spit back out during the reaction. But in an endothermic process, we have to get the energy in, and then we'll get the energy out in the case of the difference here. But overall, we're a net loss of energy from our system being put into it. It will go on to describe things that called delta G and something called entropy. But we're going to delta H. We're just going to define these things. We're not going to do any math with them. Your textbook talks about something called Hess's law, where it talks about the energy of the reaction based off of the enthalpy changes of smaller reactions being added and subtracted together. And I'll talk about that in a second. But I just wanted to go real quickly over the idea of spontaneous versus non-spontaneous. And basically the question is this little hump right here. Is that little hump going to be that's called Gibbs free energy? And so is there going to be enough Gibbs free energy to drive this reaction forward? If the answer is yes, then it's called a spontaneous reaction. If the answer is no, it's called a non-spontaneous reaction. When we are talking about spontaneous, we're also talking about something called entropy, which is extremely important for physics. And entropy is simply this: the universe moves from order to disorder. Dyslexia. What do I mean by that? Well, if you took a deck of cards, all nice and pretty, and you just set it on a table, and you came back in 5 years, would you expect the deck of cards to be a house of cards? I can't draw, so don't laugh at me. Would you expect that deck of cards to turn into a house of cards, or would you expect it to turn into a big mess? And the answer is, if you were to come into a room and you were to notice that the house of cards turned itself, or sorry, the deck of cards turned itself into a house of cards, you would be suspecting that somebody came in and played with your cards. But if you just saw it as a giant mess, then you would think that you left the window open, or that there was an earthquake, or what have you. The disorder makes more sense than the order. And that is the law of entropy, that the universe is going to constantly move towards disorder. You had a star, and the star is going to do a nova. And then that nova is just going to spread the matter all over the place. So we had high order, then we had disorder, and then we get continued more disorder. You guys can see entropy in action when you look at diffusion in a gas. So if you remember our gas simulations from PhET, when we added the different gases, the fusion, the gases don't stay on the opposite sides of the chamber unless we make them stay apart. Okay? As soon as we remove the divider, our order of green and our order of red will very quickly move to disorder. The entropy of the universe must always increase for something to be considered a spontaneous process. So some endothermic reactions can be spontaneous, but that's only when we're going to be increasing the disorder. So a good example of this is one of those cold bags. If you've ever bought like a cold bag for camping or for first aid, you basically mix it together, crack the two things together, and the chemical reaction occurs, causes the bag to get very cold. Well, what's happening is that those two salts are mixing together and they're liquefying each other as they mix together. And so even though the energy is needed to add to those two solids to make them a liquid, even though it's endothermic, because we're going from a solid to a liquid, we're changing our order from ordered to disordered, and so that becomes a spontaneous process. There are way less spontaneous endothermic reactions than there are spontaneous exothermic reactions. Things will spontaneously catch fire. They will not spontaneously get cold if their surroundings are not cold. So that's just kind of a quick, brief overview. I'm not going to have you guys calculate Gibbs free energy, which is going to be delta H, plus or minus the change in entropy. You guys aren't going to need to do that. And then the temperature. You guys aren't going to need to do that. I just wanted you to know the term spontaneous. I wanted you to know the term entropy. And then we talked about enthalpy, but enthalpy was the stuff we already talked about when it comes to H. So a spontaneous reaction occurs if your entropy goes up and your enthalpy goes down. Just how that works. But of course, temperature can cause things to be spontaneous that normally wouldn't. But again, I don't really want you guys to have to worry. So, what is Hess's law? Well, say for instance, we're interested in looking at the heat of formation, enthalpy of formation of a substance. So we're going to, burn some methane, and we're going to turn that into carbon dioxide and water. The question is, well, then how do we figure all that stuff out? And the answer is we can add up heat of formation of the products and subtract the heat of formation of the reactants to eventually come to what's in the whole equation. So in the case of this, we have water here. The heat of formation of water is going to be the hydrogen and the oxygen going into the water. So if we measure the heat of that, if we look that up, we can then use that in terms of a reaction that also contains water. Now, for the sake of Hess's law, okay, for the sake for this year, even though it's on your homework, I'm not going to put it on the test. So don't worry about doing Hess's law or the classwork. So if you go over to the module and you look at the classwork for 17, and you're looking at the practice problems here. When you get to section 4 is when it talks about heats of reaction and stuff like that. And for that, you would use Hess's law, and we're not going to worry about that. So don't worry about it. So yeah. So basically, we're just interested in the flow of energy. I want you to be able to understand how to understand those graphs, but you don't have to calculate them, okay? And then that right here, that's section 3. And then I just wanted you to understand enthalpy change, what it meant, and in terms of spontaneous, non-spontaneous, things like that. So if you look at the quiz, for today, you'll notice it doesn't ask you for too many calculations. It used to have my quizzes, and then I would click on it and it would show me, but either way. Some of you have already taken the quiz, so there you go. So yeah. This one is called thermochemistry. So it's like, what's an exothermic process? You know, things like that. This one is the enthalpy change, where they're saying, okay, how much energy would it take to produce 1 mole of nitrogen was reacted? How do you do something like that? And the answer is, you'll notice that we have 46 kilojoules of energy is what's being released. Well, that is for, it says 1 mole of nitrogen. Well, you'll notice this says 2 moles of nitrogen. So for every 2 moles of nitrogen, we make 46. So 1 mole of nitrogen would be half that, 23. That's it. And then for this, so it says, what mass of P must be reacted to produce this much energy? Well, you'll notice that 1 mole of P makes this much energy. So then you would just figure out how many moles you have from this. Let me show you that. This is kind of what they mean by enthalpy changes. So this is our chemical reaction, and it produces this much heat. Well, for every 1 mole of P4, that's how much heat we make. So there's our conversion factor. So now we have 5,905 kilojoules, and we want to know how many moles of phosphorus is that? Well, for every 2,439 kilojoules, we have 1 mole of phosphorus. But the question asks for mass, so for every 1 mole of phosphorus, we need the grams of phosphorus. So I think phosphorus is like 31 or 32, whatever your periodic table says. It's in the last unit. Hopefully you downloaded it. I will put back. I don't know why it dropped the class. I can't see it anymore. I didn't drop it. It just did that. I apologize. So if you were looking at those, I need a big one, please. Thank you. Phosphorus has the on, load. I think it's 30.9, so we'll just say 31. Because that's 32.1, yeah, so 31. So this is 31 times 4. So P4 is equal to 31 times 4. So 124. So this problem looked complicated, but it's really just 5,905 divided by 2,439. So we have 2.4 moles, and a mole is 124 grams, so 300 grams. So that's how you do that. But that's everything in chapter 17.